In this video, I'm going to talk about density log. Density log measures density or work density of the formation. And if we have some idea about the lithology and also fluid in the formation, then we are able to estimate porosity from density data. And that's the reason density log is considered as a porosity tool. I mentioned that in this course, there are two important equations that are termed as Archie's equation. To estimate SW and SXO respectively, SW is the water saturation in the Virgin zone and SXO is the water saturation in the fly zone. And these are the two most important equations that we deal with in well logging. And here we use different log data in order to obtain the parameters that are needed for these two equations. In my resistivity lectures, I explain how to estimate four important resistivities that are used in these two equations, RW, RT, RMF, and RXO. And now the only unknown parameter is phi or the porosity of the formation that you're going to learn today and in subsequent lectures. In formation evaluation, there are different logging tools to estimate the porosity. So here you may ask me a question why there are different logging tools. The reason is that each logging tool estimates the porosity with respect to a specific physical property. For example, density log estimates the porosity based on density, and neutron porosity estimates the porosity based on neutron absorption in the formation. For that reason, it is possible that each of these logging tools estimate different values for the porosity. And if we combine different data from different logging tools, not only we can improve our estimates of the porosity, but also we may have better idea about lithology of the formation and also fluid saturation or fluid type in the formation. And that's the reason we rely on different logging data in order to estimate the porosity. You're familiar with the concept of density, and density is mass over volume. And in SI, the unit is kilogram per cubic meter, but in well logging, we use the unit gram per cubic centimeter. In other words, for example, 2000 kilogram per cubic meter is equal to 2 gram per cubic centimeter. What we measure using density log is the bulk density or average density of the log. However, when we look at the log is composed of two parts, the solid part and also the fluid part. The density of the solid part of the log is called matrix density, and the density of the fluid part of the log is the fluid density. And the matrix and the fluid density is linked to the bulk density using this equation. And here, phi is the porosity. Now, just let me ask you a question. Assume that the matrix density is 2.71, fluid density is 1, and the porosity is 5%. How much is the bulk density? So you should use this equation. Yes, in that case, the bulk density is 2.62. Now just change this question a little bit. Use the same values of 2.71 for matrix density and 1 for the fluid density, but here assume that the porosity is 35%. So how much is the bulk density in this case? In this case, the bulk density is 2.11. As you see here, by increasing the porosity, the bulk density decreases. So the bulk density is a function of the porosity. And that's the reason we can use the bulk density to estimate the porosity of the formation. And indeed, we are able to estimate the porosity using this equation. And as we see here, in order to estimate the porosity from the bulk density, we have to have some idea about lithology. when I say lithology, I mean the matrix. So there are different values for the matrix density. For example, for sandstone, it has a value about 2.65. For sandy lime, about 2.68. For limestones, about 2.71, and for dolomite, 2.87. And if we assume that the formation is saturated by the fresh water, then the fluid density will be 1. So let's assume that the bulk density is 2, matrix density is 2.63, and the fluid density is 1. How much is the porosity? Yes, in that case, the porosity is 39%. You know that how we are able to estimate bulk density in the lab. So if we have like an object, if we measure its mass and also its volume, mass over volume gives us the bulk density. Okay. Now just let me ask you a question. Is it possible to measure the bulk density of rock without measuring the mass and volume? So in order to measure in order to estimate the bulk density, we need to have some idea about mass and also volume. So we have to measure them. Is it possible to estimate the bulk density without having the mass and volume or without knowing them? Yes, it is possible. And this is based on gamma ray absorption. If you remember in my gamma ray lecture, I talked about a calibration facility at the University of Houston in Texas. And I talked about some standard condition to calibrate gamma ray logging tools. And I said that, for example, there is a standard drill mod. So if in the field or in the real scenario, our drill mod is heavier or lighter than the standard drill mod, so we have to apply some corrections. For example, if the drill mod is heavier or is denser than the standard drill mod, we're going to end up underestimation of the gamma ray because gamma ray is more attenuated in denser material, and that's the reason. So we have to apply some corrections to our gamma ray data. Okay. In other words, something that we can use in order to estimate the density of the formation is by looking at gamma ray attenuation in the formation. What you see here shows a schematic of density logging tool. So density logging tool is composed of a source that produces high energy gamma ray, and the source is cesium-137. It's a kind of radioactive element that produces high energy gamma ray. And the gamma ray travels through the formation, and as you see here, we have two detectors, and these two detectors detect the gamma ray and count the number of them. And here, as you see here, there is a caliper that helps the gamma ray tool to clamp to the formation. In addition, this caliper also measures the borehole diameter. I'm going to talk about it later. Now, assume that the formation has low density. Low density means higher porosity, and in that case, we're going to have higher detected gamma ray. On the other hand, if we deal with high or denser formation, in that case, the gamma ray will be attenuated more, and so we're going to detect lower number of gamma ray. So this is how we are able to estimate the density of the formation based on the number of detected gamma rays. Something that if you should have noticed here is that the standard gamma density log has two detectors instead of single detector. And here is the question. Why does the density logging tool have two receivers or two detectors instead of one? So the answer is to mitigate the effect of the unevenness of the borehole wall. Just let me explain this situation. In old days, the density log used to have just single detector, and observations confirm that with that logging tool provided wrong estimates of the density in the case of uneven borehole. And the reason is that the borehole surface is not even, and it has some roughness, some unevenness. And as a result, for example, it is possible that due to the unevenness, it is not this unevenness, it is not clamped to the formation perfectly. What happens here, a fraction of the gamma ray will directly travel from the source to receiver without going through the formation. And as a result, we're going to have a wrong estimate of the density. So what I mean, if the formation wall was perfectly flat, we didn't have any issue to have just one single receiver. But in reality, this is something that we have. So in reality, the borehole wall is uneven, and as a result, the clamping may not be perfect. And for that reason, we're going to have wrong estimate of the bar density using single detector gamma ray. Here, I'm going to explain how two detector gamma ray works and why it is robust to estimate the density of the formation in the case of uneven borehole wall. Now, what we measure indeed in order to measure the porosity, what we do in practice, we measure the number of the gamma ray that are recorded by near gamma ray over the number of the gamma ray that is detected by far gamma ray. So here is near gamma ray and here is the far gamma ray. And assume that the formation density is 0. If we assume that the formation density is 0, in that case, the two detectors will record the same number of gamma ray. And what we should expect here is that this ratio should be 1. Now consider another scenario that the density is very high. In that case, the far gamma ray will record lower number of gamma ray compared to the near detector gamma ray. And the reason because the gamma ray has to go through a longer route to get to the far detector. And for that reason, gamma rays are more attenuated. So if we have high density, in that case, this ratio will be greater than 1. So the greater the ratio becomes, it means that the density is higher. And this is how we are able to infer the density from the ratio of near detector over the far detector. And this is how we are able to estimate the density. So why this method is more robust to estimate the density in the case that the borehole wall is not even? So the answer is very simple. Because here we calculate the ratio instead of the number of gamma ray directly, somehow the effect of the unevenness of the borehole wall is mitigated because we measure the ratio, not the number of detected gamma rays. What you see here is an example of, as an example of real data. The blue curve is SP log, and the red curve is gamma ray log. And the dash curve, as you see here, is the caliper or the measurement of the borehole diameter. And if you look at the range here, it shows that the borehole diameter varies from 10 inches to 20 inches. So it is the range of the borehole diameter. So here you see that we see a shade zone, and the shade zone we can consider to be the impermeable zone. And from here to here, this area, the layer is permeable. And if you look at it here, you see that, for example, in the shade zone, the borehole diameter is about 14 inches. And here, when the formation becomes permeable, the borehole wall diameter is about 12 inches. From this observation, I can conclude that there is a strong correlation between the borehole wall diameter and the state of the permeability of the layers. And that's the thing. Indeed, caliper is kind of a permeability tool. And that's the reason they're put in the same track that we show gamma ray log, SP log data. In well logging, usually we put the logging data that provide us with the same information in the same track. So here you see that in the first track, track number 1, what you see here is the depth information. In track 2, you see 3 logging data. The blue curve is SP log, the red curve is gamma ray, and the dashed curve is caliper. So as I said, because these 3 logging data give us some idea about the state of the permeability of layers. And in the third track, you see the values of the resistivities, the 3 readings of the resistivity. And in the fourth track, you see we have, again, 3 curves. The one thing that you see here is the green curve. That is the neutron porosity, or phi n. And then you see we have the red curve, that is density data, or rho. And the dash curve is P, or a specific photoelectric absorption constant that I'm going to talk about it in this lecture. And in the fifth track, you see the information about lithology of the formation. For example, here shows that we deal with shaly sandstone formations. Something that is interesting here, if you look at it here, it shows the range of the porosities. So it shows that the porosity varies from -15 to about 0.45. And you may ask me a question, what is the meaning of the negative porosity? So why we have negative porosity here? We know that the porosity has a range from 0 to 1. In other words, in the nature, we never ever can find a formation with negative porosity. So what is the reason here the value, a negative value for porosity is indeed predicted? In order to answer this question is that because sometimes we may have some wrong assumption about the matrix or lithology of the formations, we may end up a negative value for the porosity. Okay, so for example, assume that the formation is limestone, but we assume the formation to be sandstone. In that case, we may end up a wrong estimate of the porosity or negative value for the porosity. Or the rock is not pure. So, for example, we deal with limey sandstone, and we didn't consider the effect or the presence of lime. And in that case, again, we may end up obtaining a negative value for the density, for the porosity. Okay. And these are some examples, if you have wrong assumption about lithology, or you don't consider the impurity within rocks, then we're going to end up negative value for the porosity. So how we are able to correct it is that by having the correct assumption about the lithology. By considering the real lithology of the formation, then we can correct the estimate of the porosity and get rid of that negative value. I've copied the previous example here because we're going to need it later for this example. Now let's do, some calculations here. Let's go back to the above example. So assume that the bulk density reported 2.69. Now, how much is the porosity based on the wrong assumption of the formation density to be 2.65 and assume that rho f is 1. So what I want you to do here is that, so assume that this value of the bulk density is reported by, but we have a wrong assumption about the matrix density. So we assume that the formation is purely sandstone and we don't consider the impurities of the sandstone. Now, how much will be the porosity if you have negative assumption about lithology? So as you see here, in that case, the porosity will be minus 0.02 or minus 2%. So this is an example that because we had wrong assumption about the lithology, we ended up a negative value for the porosity. Now for the same example, if the bulk density again is 2.69, how much is the porosity based on the corrected value of the matrix density? Now assume that again we have the same scenario, okay? But here we assumed correct lithology and based on that, estimate the porosity here. So you see that once we use the correct value for the matrix density, or we have corrected our assumption about the lithology, then we're going to end up the porosity to be 0.02 or 2%. That is a reasonable value for the porosity. Something that you should notice here is the effect of gas. And gas has very low density. And if we don't consider the effect of the gas and we assume the formation is saturated by water or oil, again, we're going to end up a wrong estimate of the porosity using density logging tool, okay? So in other words, in order to have a correct estimate of the porosity, not only we should have a correct assumption about lithology, but also we should have a correct assumption about the fluid in the formation. So if the formation, if the fluid formation is gas, and if wrongly we assume it to be water, then we're going to have problem. And the problem is that if you look at the equation here, phi is equal to rho ma minus rho b, rho ma minus rho f. So if we have gas saturation in the formation, it means that the bulk density will be very, very low. So if we wrongly assume the fluid density to be 1, in that case, we're going to obtain very, very overestimation of the porosity. In practice, it is possible that we have some hydrocarbon saturation in the formation, and in order to obtain a more accurate estimate of the porosity using bulk density, so we have to calculate the average of the fluid density in the formation, and we can use this equation. Here SXO means the water saturation in the phylloxton, RMF is the density of mud filtrate in the flux zone, SXO. S oil means the oil saturation in the flux zone. Raw oil means oil density here. S gas means gas saturation in the flux zone. And raw gas means the gas saturation in the flux zone. So something that is noticeable here is that why we use SXO here or RMF, the density of RMF or mud filtrate. And the reason is that the penetration of gamma ray is very shallow. So in other words, gamma rays don't penetrate the transition or virgin zones. And mostly the density log provides us with information about the bulk density in the flux zone. And that's the reason we should use SXO here, that is the water saturation in the flux zone. And again, notice that here we have SXO plus S oil plus S gas should be equal to 1. Now, having said that, so assume that these values are reported. SXO is 40%, S oil is 5%, raw MF is 1%, raw oil is 0.85, and assume that the gas density is 0.18. How much is the average of the fluid density for this scenario? Yes, the average of the fluid density will be 0.5. How we are able to do that? First of all, I estimate gas saturation, and gas saturation is given by 1 minus SXO minus S oil. Now, for this example, it is 55%. And then I use this equation in order to estimate rho F. And if I do that, I'm going to obtain 0.5 for the average of the fluid density in the formation. A more advanced version of density log is also available, that is called litho-density log. So litho-density log not only measures the density of the formation, but also it helps us to have some idea about the lithology of the formation. So in other words, not only it measures the density, but also it gives us some idea about lithology. So how we are able to do that? We can identify the lithology based on the energy of the gamma ray. So the gamma ray that is produced by the cesium 137 has very high energy. So if we measure the energy of our emitted gamma ray, we're going to notice that all of them will have energy about 0.662 mega electron volt. But what happens in the end, assume that this is the number of detected gamma ray. Okay, but when the gamma ray travels through the formation, their energy will be attenuated. So assume that we not only we measure, we count the gamma ray, we detect them, but also we measure their energy. If we do that, and if we plot the number of detected gamma ray versus their energy, then we're going to end up a curve like that. And this curve is indeed shows the energy spectrum of the detected gamma ray. And we can use this curve in order to identify the lithology of the formation. So here is just what I mentioned here. So as you see here, A is the energy at the source location, cesium 137, and all of the emitted gamma ray has the energy about 0.662 mega electron volt. But once the gamma rays travel through the formation, their energies are attenuated. And if we plot energy versus count rate, we're going to end up a curve like that. So what you see here shows the energy spectrum for three lithologies: sandstone, dolomite, and limestone. And what you should notice here that the density of these three formations are the same. So the bulk density is the same, but something that are different here is the lithology. So something that is interesting here, these three lithologies have identical energy spectrum from about 0.25 to about 0.6. And the three lithologies shows the same trend, the same curve. And indeed, what you see here, this is called hard gamma ray window. So hard gamma ray window is indeed high energy gamma ray. Those gamma rays whose energy is greater than 0.25 mega electron volt. And we can use these gamma rays in order to estimate the density. So if you look at here at lower energies, these three curves are different. For example, some what I'm highlighting here is the energy spectrum of limestone, and here shows the energy spectrum of dolomite, and here energy spectrum of sandstone. And this is very interesting. So at lower energies, these gamma rays, these curves are different from each other, or the energy spectrum at lower energies are different from each other. And we can use, indeed, we can use low energy gamma ray in order to identify the lithology. So what I mean we can use the gamma rays whose energies are smaller than 0.25 mega electron volt to identify the lithology as, and indeed, this is called soft gamma ray window. So soft gamma ray window is indeed are those gamma rays whose energies lie between 0.02 to 0.06 mega electron volt. So we use these low energy gamma rays in order to identify the lithology. So how we are able to do that? If we measure the number of detected gamma ray within this low energy range, we are able to estimate U index, and U is indeed volumetric photoelectric absorption index. Okay, so in other words, if we measure the number of gamma ray within this range, we can estimate U, and U is volumetric photoelectric absorption index. And volumetric absorption index is a function of density and a specific photoelectric absorption index, or PE. So indeed, if we have some idea about the density of the formation, and if we measure U, then we can estimate PE, okay, or the specific photoelectric absorption index. That is the property of the material as is, and we can use that value in order to estimate or identify the lithology. So what you see here, PE is a material property. Limestone, sandstone, dolomite can be differentiated from each other with respect to their unique values of PE. So what you see here shows the values of PE for different lithologies. For example, if you look at calcite or dolomite, calcite or limestone, the value of PE varies from about 5.08 to 4.7. For quartz or sandstone, the value varies from 1.81 to about 1.54. And doesn't matter what porosity we are, or if we have gas in the formation or water in the formation, you see that these three, the values of PE are different from each other for each of these lithologies. So this table shows the value of PE for different rocks. For example, for barite, the value is 266.82. For hematite is 21.48. And for magnetite, the value is 22.24. And you see that we have wide range of PE for different rocks in the nature. And as you see here, the value of PE is usually placed in the same track along with density log and neutron porosity log. For example, here for this example, it shows that P varies from 0 to 20. And for this specific example, the value of P is about 2.66. That is close to the PE value for shaly sand. And if we go back to this chart, it says that for shaly sand, the value of P is 2.7. So it means that the value that we get here is very close to the real lithology. And from the lithology track here, you see that we deal with shaly sand in this example. So something that is interesting here is that using P, we may get some idea about lithology. However, we should be careful about that. And the reason, because rocks may have some impurities. Okay, for example, we deal with shaly sand or we deal with limey sand. And due to those impurities, we may get different value for PE. And if we don't consider those impurities in rocks, in the formation rock, we may end up a wrong identification of lithology. So what I mean, PE can help us to have some idea of lithology, but it is not conclusive itself. So we have to use other prior information that we have. For example, we can use drill log cuttings, we can use core samples, and etc. geological studies. And if we integrate the background information with P, then we can interpret P, more accurately. But if just you want to rely on PE, it is very problematic, because, as I said, it is possible that rock has some impurities, and for that reason, we end up very different values for PE. And for example, you obtain PE to be 3 and you consider a specific lithology, but in reality, for example, you have a limey sandstone, for example. These are the things that you should consider when you interpret P. So never ever rely on PE itself. And in order to improve your interpretation, integrate your PE values with background information that we have from, for example, core samples, drill rock cuttings, and geological studies. I hope that you have enjoyed the lecture today and have some idea about how we use density data to estimate the porosity. And thank you for your attention.